Welcome to the course on nonlinear dynamic systems and control. My name is Vijay Sekhar Chalaboyna and I'll be the lecturer for this series of topics on nonlinear dynamical systems and control. Before we jump into the actual course, we will go through some motivational examples. One of the key concepts that's quite important for control systems is the so-called feedback. The first example is something that we are all familiar with. It's a flush toilet that's probably installed in every one of our houses. The history of this is 500 years old. Specifically, flush toilet was invented in 1500s, but the main mechanism that is used is the so-called floating ball mechanism for controlling the water level is more than 2000 years old, and the floating ball mechanism in such a way that basically whenever there is less water, it opens up and the valves opens up and then water flows in, and whenever the water is at a particular level, the floating ball actually closes the valve. It is a beautiful system, ingenious system that uses the principle of basically a floating ball floats whenever there is water touching it, and that becomes a sensor for the level of the water, and it's connected to the valve in a way that basically whenever the water pushes the floating ball up, the valve closes it automatically, closes by itself. And so you have a sensor and actuator. So that's essentially every feedback system or every control system will typically have. You will have a sensor for something. In this particular case, the variable of interest is level of water. So the floating ball does the job of actually sensing the level of water. Now, how do we change the level of water? By adding more water, and that comes from the valve, of course. If the valve opens, then more water comes in. If the valve closes, it doesn't add any water. And of course, in this flush toilet mechanism, there's a water outlet, and that's what actually requires this adding water and then through valve and actually automatically closing it. So in fact, that word automatic is quite important in any of the things that we speak about in this course. Most of the time, we will be more talking about analysis, but whenever we speak about control, we actually mean automatic control, things that automatically decide on their own what to do. In this particular case, the floating ball in some sense automatically closes the valve whenever the water is at a certain level, and it opens up whenever the water goes below a certain level. So there are many such examples. The second one that I chose to describe is the so-called James Watt governor. This is another instrument that was essential and part of the first industrial revolution. James Watt invented the steam engine to essentially transfer the manual labor, the severe, very energy demanding manual work is transferred to the steam engine, and in order to ensure that the steam engine is controlled well, specifically the speed of the engines that are run on steam engine are controlled in a certain manner, this particular governor was invented by James Watt. Again, it is an ingenious system. There are two fly balls, they are called, and whenever the system actually reaches a certain speed, the fly balls, more or less using the principle of conservation of momentum, they go in and out with respect to the center, and whenever they go away from the center, there's a mechanism that will stop the steam coming in, and then whenever it closes, more steam comes into picture, and then basically increasing the speed. So again, you have a sensor and actuator, and in most of these cases, the entire mechanism is such that whenever the sensing happens, the actuator automatically does something. The third example is not man-made. It's something that we find everywhere in warm-blooded animals. Specifically, even human beings, we actually have this particular system inbuilt. This particular system is evolved over millions of years, and what I'm talking about is basically how our body controls the temperature at a particular number. We all believe that the average temperature has to be around 98.4 degrees Fahrenheit or 37 degrees centigrade. So how does our body do it? And all of us learned as children that basically this happens whenever there is ambient temperature that's more than much more than that we can handle, and the body will start sensing that, and then in order to maintain its own temperature, it starts sweating to the point where the sweat evaporates and it cools down the body. Different animals have different mechanisms of cooling themselves. For example, dogs put their tongue out, and the saliva on the tongues basically essentially reaches a point where it evaporates, cooling down the temperature there. And in all this, of course, in this particular case, the sensing is probably done by the skin in the case of humans, and then that signal actually goes to the brain, and then brain sends another signal to actuate the sweat glands to sweat, and so on and so forth. Biological systems in general have many such feedback mechanisms, and all of them are quite complex. This is one of the simplest things that we can at least try to understand, but if we want to really analyze, they're not the simplest of the systems, but then they have inspired many man-made systems, and they're in a world in itself. So the last one is more important from a applications perspective. Man never thought that he could fly, but in 1912, Wright brothers actually managed to make a machine that actually could fly. And in all this, one of the most important things is the control system. Without a feedback control system, they couldn't have even made a first flight. And the mechanics of flight and how the control works is actually quite intriguing and very complex, and we're not going to get into any of the details here. Some of us probably know that in the case of an airplane, we have things like ailerons, flaperons, and whatnot to change the direction of the flight and things like that. So these are typically they're called control surfaces because they can actually control the direction of the aircraft. And of course, we have engines that provide power, and the shape of the wing is important. Everything becomes important, and there's not a single system there, but it's an entire a combination of many systems there. You have fluid mechanics, solid mechanics, everything, propulsion systems, the entire thing is controlled these days by computers and of course a lot of electronics. It's a highly complex system and quite an important system for anybody who learns controls. These are just 4 examples that I put forward to understand the importance of feedback. Feedback is everywhere, and in very complex examples or very simple examples, in all these basically you have 3 components: sensors, actuators, and of course how the two things, sensors and actuators, are connected to one another. But let me just briefly go through a list of things that what this course is about and what this is not about. This course focuses on nonlinear systems, not so much on linear systems, although linear systems become a special case of nonlinear systems, and we will look at linear systems once in a while as a special case or sometimes motivation. but the objective is actually more about nonlinear systems. And the primary goal here is actually analysis and not so much on control design. Control design becomes an afterthought. Other way of looking at it is actually control design is quite complicated. If we can analyze, we can use that knowledge to design controllers, but it's not the easiest thing to do. We use MATLAB once in a while to show simulations and actually assign homework and stuff like that, but we do not focus anything really on MATLAB in this particular course. Once in a while we'll talk about applications, but only as a motivation, but the application does not become the focus. So the starting point for most of the analysis here is that somebody gives us a model. Somebody gives us these sensors and actuators. So for example, in the flush toilet case, the floating ball mechanism and the valve and things like that are assumed to be there by somebody gave us, and we only look at how to analyze that particular system rather than inventing specific sensors and actuators to do a particular controls task. It's not mandatory, but it's always advantageous to have some exposure to classical control systems, and even better if you have some exposure to linear systems. So before we jump into the actual list of topics that are covered in this particular course, I want to just have a question for all of you. Imagine you are driving a car. The question is, what are the control problems and what are the sensors and actuators? This is just as a thought experiment. It's important to keep thinking in terms of why we are learning control systems. It's eventually to design things like driving a car and solving control problems. So the answer to this particular question is, of course, again not so simple, because even in a car, just as we have seen in a flight control system, there are many different control systems. The standard ones that we can think of are the simpler ones are speed control. Many of us probably know how to drive a car, and especially with cars that have cruise control, which essentially are is a system that has automation. Certainly there is an automatic mechanism to control the speed at a particular number. We typically, what we do is we set a number, and then basically the car maintains that particular speed. How it does it? Well, in the case of a car, to increase the speed, we have of course accelerator, and to decrease the speed, we have brakes. And of course, to sense the speed, there are speed sensors, and using these various components, you can design an algorithm to essentially maintain a particular speed. There are other standard control problems that come into picture. These days, there are cars that do everything automatically, but most of the time, we as drivers take care of that, including speed control if we don't switch on the cruise control. The standard one is, of course, to ensure that we stay on the road, go on a specific path, and we use our eyes as sensors to sense the direction. And of course, the steering is there to ensure that we can actually give the command to the car to move it into the right direction. If we are moving away from our path, then basically the steering wheel can be used to actually put us back in the right direction. So how we do it in terms of whether we use just the visual information that whether we are exactly on the path, or do we use any rate of change of that change of the direction? All those things are very complicated questions, and we don't have clear answers how humans control these cars, but we can actually control these things through automatic mechanisms. That's obviously how some of these self-driving cars do. So that brings us to the list of topics that we are going to cover in this particular course. The first lecture or so, first week, we'll go through introduction, preliminaries, and doesn't get into quite so much of technical aspects. In the second week, where we actually get into quite an important topic in terms of solutions to certain models. Specifically, we focus a lot on ordinary differential equations, and in the third week is where the real topics of this particular course start. There is a concept called stability that is quite important, and there are different types of stability, and we will go through all of them, and we will go through many results that actually verify stability of a particular system, and we will certainly go through many theorems. And there are extensions to some of these theorems, and without getting into details, basically we will go through that in the fourth week. And the fifth week is where we will specialize some of these things to linear systems, and that becomes quite an important aspect of nonlinear systems, where we use linear systems approaches to still address the question of nonlinear system stability. And finally, in the part 1 of this particular course, we will briefly touch upon an important topic called construction of Lyapunov functions. So this entire course, the first part, is dependent on our ability to find a Lyapunov function, and it satisfies certain properties, then we can conclude stability. However, finding Lyapunov functions is not the easiest, and we cover some basic classes of systems where we can find Lyapunov functions in week 6. So this is a first part of the course where mostly it's analysis of models. In the second part of the course, we will actually look at the results that we developed in the first part, and still going to be a lot of analysis, but applications of what we have learned in the first part. And in the week 7, basically we will go through something called Luray problem and applications of Luray problem to robust stability. These are quite popular in linear systems. For example, structure and sector uncertainties can be looked at in this particular topic, and a more generalization of all these topics is covered in something called passivity and dissipativity. Essentially, in the first part, we look at only systems with no input, we call them autonomous systems, and in the second part, we will look at systems with input and output, and that's what is covered typically in this passivity and dissipativity chapter in week 8. And then in week 9, we will actually look at control examples, specifically something called adaptive control, which is quite useful in applications. There are 1 or 2 different types of adaptive control, and we will discuss all those things in week 9. And in week 10, we will see how all this theory apply to general control problems. Again, linear systems and linearization become important, and specific classes of systems called cascade systems become important. And finally, we will look at optimal control and inverse optimality. And the course will be ended with a general discussion on model-free approaches to control. So this is essentially what is going to happen in the next 10, 11 or 12 weeks. And though we won't talk so much about control design, we keep reminding ourselves that we are learning all these things for the sake of understanding control design. So the next question for you is basically, what are the various steps involved in a control design, right? So what is an approach to designing control systems? One of the first things that we need to understand is the goals of a typical control system. I mean, the goals of control system can be many, and we want to make sure our car is running at a particular speed. That could be one goal, or maintaining a certain direction, or both of them, right? So when we have 2 goals, how do we maintain which is more priority, or both of them important? These are the various questions that we get. But of course, once we have an objective, suppose if we want to maintain a particular speed, the least we should know is what is our current speed, right? And therefore we need a sensor to detect speed at the least. followed by, of course, ability to influence the speed, ability to change the speed of this particular system, and that typically comes in the case of car in the form of brake or an actuator, brake or an accelerator, and these are the things that can affect the system are called actuators. So these are the bare minimum things that we need, sensors and actuators, and then not arbitrary sensors and actuators, but the sensors and actuators that are quite related to the goals of the control system. And of course, we have to know how to connect these sensors and actuators. That's what is all about the control design aspect. Once we know how to achieve the basic goal, that is specified as objective for your control system, we can get the basic job done. Then the next question comes basically, can we optimize the control? And of course, that's where the question of what do we mean by optimization? What is our performance to maximize, if there is any risk involved, or is there anything negative thing involved? How do we minimize that? For all these things, we need to understand what is called a performance, right? And like any engineering system, if we develop a mathematical model of the overall system, then basically we can do a lot of groundwork before we actually implement on an actual system. And this course is all about not developing mathematical models, but using mathematical models. Can we achieve certain goals? Can we achieve optimization of a particular performance, and so on and so forth. So once we have a mathematical model, we perform analysis and design using appropriate methods. The design in this particular case is what is that automatic feedback mechanism that will achieve the particular objective of the control system. And of course, like any design, we can verify these things through analytical methods in certain cases. Some cases are so complicated that simulations become the simplest way to do it. These days, the simulations are so powerful that we can simulate pretty much any system. And of course, once we are satisfied with simulation results and analytical results, then we can actually go to the actual system, and then we always find something not quite so accurate there, and then we go back to the blackboard and then iterate, right? So that's part of any design system. So just to summarize, basically designing a control system, we start with basically developing a mathematical model for this entire system, assuming that the system has appropriate sensor and actuators that are appropriate for the objective of the control system. And once we have the mathematical model, we design a control system and we analyze that particular control feedback. And of course, through simulations, we can further verify, optimize wherever possible, and iterate if necessary.